So in this video we are going to discuss the question which appeared in IIT-JAM 2005 examination. So we are going to discuss the question in thermal and statistical mechanics. The first question is the molar specific heat of a gas as given from kinetic theory, it is 5/2R. So we are given molar specific heat C, which is equal to 5/2R. Okay. If it's not specified whether it's Cp or Cv, so it's not given to us whether it's a Cp or Cb, so one could conclude that the molecule of the gas, okay, so out of these four options we have to identify that for which one particular case the molar heat capacity, it comes out to 5/2R. It could be Cv or Cp. Okay, so let's first continue with the monatomic gas. For monoatomic, okay, so we have 3 degrees of freedom, basically 3 translation degrees of freedom. So that means I'm writing that as FT, where T stands for translation. This is equal to 3. So we know that there is no rotational degrees of freedom for the monatomic gas. So here from FT is equal to 3, so this implies that average energy per mole, that is equal to E, that is equal to F/2 NA kb T. That's the per mole. Okay, basically. Okay, so here F is equal to 3. Okay, so NA, that's the Avogadro number here. This is Avogadro number. Okay, so this product will give us R. Okay, so therefore the average energy per mole for monatomic gas, that is equal to 3/2, and Na multiplied by kb, that will give us R, and then T. So this means the heat capacity at constant volume, that is equal to dE by dt, and that turns out to be equal to 3/2R. Okay, now from here we can immediately calculate the Cp, that is equal to Cp minus Cv, that is equal to R per mole we are talking about. So that means Cp is equal to Cv plus R, and then when you put the value of Cv here, you will obtain 5/2R. So that's the our result, it's matching with one of the options. So it could be a monatomic, but let's see whether the result matches with some other option or not. Okay, so the second case that we are going to talk about, a diatomic gas molecule. Diatomic gas molecule. So here we will have two options. Either it could be rigid diatomic, and the second option could be non-rigid. Okay, so let's we will try to understand the consequences of this rigidity and non-rigidity, or non-rigid diatomic. Okay, so when we are talking about a rigid diatomic, for instance, let's talk about a gas molecule having two atoms, but when this bond, it is rigid. Okay, so that means no vibrations. When this bond is rigid, so that means no vibrations. Okay, and when it's non-rigid, okay, so in that particular case, the vibration degrees of freedom, they will also come in. We need to take into account the vibrational degrees of freedom also. Okay, so that makes the difference here by using the word rigid and non-rigid. Okay, so let's first talk about the rigid diatomic. Okay, so the first case, that is when we consider that we are having a rigid diatomic, so in that case, a rigid diatomic molecule, okay, so it will have the translation degrees of freedom, it's same 3, and how many rotational degrees of freedom? We will have 2 here. Okay, so only 2 rotational degrees of freedom we need to consider, and there will be no vibration. When it's rigid, no vibrational degrees of freedom. Okay, so that means Fv, that's equal to 0 here. So total the average energy for the diatomic molecule, if we consider the translation and rotational degrees of freedom, okay, these are so total will give us 5. So 5 multiplied by 5/2 R T. Okay, so that means Cv here, Cv will be 5/2 2r, but CP will be 7 by 2r here. Okay, so if we consider the rigid non-rigid diatomic, so in that case the difference will be here non-rigid and diatomic. So in this case we need to consider the vibration degrees of freedom also. So vibration, when you consider the vibration between this pair, so here we will have a contribution for the kinetic energy and plus potential energy. Okay, so then we will have one square energy term corresponding to kinetic energy and another squared energy term corresponding to potential energy. So therefore two degrees of freedom will appear here, two additional degrees of freedom will appear here. So FV, that will be 2 here. Remember that in a few books it's considered as only 1 degree of freedom, and then we take a contribution of 2 basically, and that contribution of 2 basically originates from these two different energy terms. One from kinetic energy that originated because of the motion of these two gas molecule, and the potential energy term, that's because of the storing force that comes into play between these two molecules. Okay, so we will have two terms here, two square energy term here. So the total average energy will be in this case sorry, by assuming 3 translational, 2 rotational and 2 vibrational degrees of freedom, so that will be 7 by 2 R per mole. Okay, so therefore this case doesn't come into the picture in the framework of the question which is asked here. So therefore what we conclude is that if we consider a monatomic gas molecule, then Cp turns out to be 5 by 2 R. Okay, and when we consider a rigid diatomic gas molecule, then its Cb which is 5 by 2R. Okay, so therefore correct option here is it could be a monatomic or rigid diatomic gas molecule. So let's continue with the next question. The question is, the value of the entropy at absolute zero of the temperature would be 0 for all material, finite for all material, 0 for some material and non-zero for others, unpredictable for any material. So this is basically a conceptual question, and it's really important to know, because if you just take a look at the earlier books, so then the answer should be 0 for all material. But right now according to the present understanding of the properties of the various materials, let's try to understand. I'm going to cite here a particular example where the entropy at absolute zero, it's not basically zero for all material as predicted by the third law of thermodynamics basically. Okay, so the example that I'm going to talk about here, it is the example of a carbon monoxide, it is CO. So this gas molecule at absolute zero, either it could stay as CO in crystalline form or as OC. Okay, so that means if we consider a situation at absolute zero, where we consider that the system acquire a unique configuration, and in that particular situation the number of microstates which are accessible to a system, that's only 1. Okay, and based upon this discussion, we conclude that in general S entropy, that is equal to Kb ln omega, and that will give you 0 entropy for all material, irrespective of the fact whether we are talking about solid, liquid or gases. But this is a very special case, so that's why I will request you to please pay attention to this particular example, because many times the question has been asked on this particular example. Okay, so let's try to evaluate what is the entropy of this gas molecule at absolute zero, then it exists in the crystalline form. Okay, if we assume a system having n number of gas molecule, so at absolute zero it's possible that ny2 gas molecule will exist as CO and ny2 molecules will exist as in OC form. Okay, so therefore the corresponding number of microstates at absolute zero will be a total number of gas molecule, that's n factorial arrangements, out of which ny2 molecules, they are aligned like CO, so n by 2 factorial arrangements, and then n minus n by 2 factorial, that will give us the n by 2 factorial again. Okay, so therefore the entropy from here we can easily calculate by this Boltzmann equation that we just used here, S that is equal to Kb ln omega, and that is equal to Kb ln n factorial divided by n by 2 factorial n by 2 factorial. Okay, so now let's try to evaluate this quantity, the logarithmic of the microstates. Okay, so ln omega that is equal to ln n factorial minus 2 times n by 2 ln n by 2 minus n by 2. Okay, so here we have made use of the Stirling approximation by assuming that n it's very large. Okay, so after the okay, so here we can write ln n factorial as further n ln n minus n. So this is by using the Stirling approximation, and the second term can be rewritten as, so this will give us n ln n by 2 plus n. So this n will cancel with n, so we are left with n ln n minus n ln n plus n ln 2. So this will cancel with this, so ln omega is equal to ln n ln 2. So therefore the entropy turns out to be equal to entropy that is equal to n kb ln 2. Okay, so if we assume that n is equal to the Avogadro, if we calculate the entropy per mole of the carbon monoxide, so then this n will be equal to Avogadro number of molecules. Okay, so that is equal to r ln 2. Okay, so which is greater than 0. So therefore here what we conclude is that for most of the substances the entropy at absolute 0 it's 0 for some materials and non-zero for others. So here the example that gives a non-zero entropy at absolute 0, that's the example of carbon monoxide. So option C is correct here. So let's continue with the next question. The statement is which one of the following statement is incorrect? So out of these 4 statements we have to identify the incorrect one. Okay, so let's try to understand. Let's go one by one. Indistinguishable particles obey the Maxwell-Boltzmann statistics. Okay, so in Maxwell-Boltzmann statistics the particles they are treated as distinguishable. Okay, so that means the given statement it's correct. Let's see if there is another statement which is wrong. Option B is all the particles of an ideal Bose gas occupy a single energy state at absolute 0. Yes, that's true. It's true. Okay, the integral spin particle obey the Bose-Einstein statistics. Yes, that's also true, because the Bose-Einstein statistics that's obeyed by particles having integral spin. Okay, integral spin. And proton obey the Fermi direct statistics. Yes, that's true. Electron, proton and neutron, all these are called as fermions, and these are half integral spin particle, half integral spin particles. Okay, so that means they obey the Fermi direct statistics. So therefore the correct option here is, or in other words you can say that this is the incorrect option. Okay, but according to question this is the right option. Okay, so A is correct here. Let's take a look at the next question. The statement is establish the equation du that is equal to du by dt at constant volume dt plus t dp by dt minus p dv. So given that du that is equal to tds minus pdv, and one of the Maxwell relation, that's ds by dv that is equal to dp by dt, where all these parameters that is u, p, tv and s they have their usual meaning. Okay, so further, if the specific heat is taken to be independent of T, so then utilize the above equation to derive an expression for the UTV for 1 mole of a van der Waals gas and then obtain corresponding expression for the ideal gas. Okay, so let's continue with the part A first. Okay, so for this purpose we will make use of the first law of thermodynamics. Okay, and then and also the given information in the question. Okay, so from first law, so I'm continuing with first part. From first law, we have du that is equal to TdS minus P dV. Okay, let's call this as equation 1. So now we will assume here, let entropy be a function of T and V. Okay, so from this information we can write ds that is equal to ds by dt at constant volume plus ds by dv at constant temperature. So let's call this as equation 2. Okay, so now we will put the value of ds from equation 2 in equation 1 here. Okay, so if you do that, so that means 1 and 2 they implies du is equal to t ds, t multiply by ds, which is ds by dt at constant volume dt plus ds by dv at constant temperature dv minus p dv. Okay, so we will separate some of the terms here. So the terms with the coefficient dv, we will keep them together, and the term with dt as coefficient, we will separate that term. So t ds by dt at constant volume dt plus t ds by dv at constant temperature minus p, and all these two multiply by dv. Okay, so we will call this as equation okay, so let me call this as equation 3. Okay, now so this can be rewritten as, so here I'm going to make use of some of the important results. So let me first discuss with you, and then I will rewrite equation 3 in a more general form. Okay, so TDS by dt at constant volume. Okay, so in principle TDS that is equal to dq. That's the mathematical statement of the second law of thermodynamics basically. So this can be rewritten as, so this is equal to dq by dt at constant volume, and this is in principle further equal to du by dt at constant volume, and this is equal to Cv. Okay, so why this equivalence, it stems from the first law, du that is equal to du is equal to dq minus pdv. Okay, so from here we learn that du by dt at constant volume that is equal to dq by dt at constant volume, and that's nothing but Cv, because here in at constant volume this term will vanish, so the du will be dq in that case. Okay, so that's how we obtain this result. Okay, and another important result that we are going to use here, it's also given in the statement, that is the one of the Maxwell relation. So we will make use of this this equation here. So we are going to replace this. Okay, so with this information and this information, the equation 3 can be rewritten as equation 3, so that means du that is equal to du by dt at constant volume multiply by dt. Okay, plus t ds by db. So ds by db we will replace with dp by dt. Okay, plus t dp by dt at constant volume minus p, and then multiply by dv. Let's call this as equation 5. Okay, so now for the van der Waals gas, so we'll obtain the results for the van der Waals gas and the ideal gas. So for the first case in part B, the first corresponds to the case of van der Waals gas. we have the pressure that is equal to RT upon B minus B minus A upon B square. This implies dP by dt at constant volume is equal to R upon B minus B. Let's call this as result 6. Okay, so 5 and 6. So 5 and 6. What is 5? That's an equation that we just discussed. Okay, this equation. Okay, so we will substitute the value of dP by dt here and then see what we are getting. Okay, so this implies du is equal to du by dt at constant volume dt plus t dp by dt. So dp by dt is R upon B minus B, so that will give you RT upon B minus B minus P. So minus P is what? P is equal to RT upon this one. Okay, so minus P, so I'm replacing P with this result. Okay, so RT upon B minus B plus A upon B square multiplied by dV. So this will cancel. So ultimately du is equal to CV dt plus A upon B square dV, and this upon integration, so that will give you a delta U that is equal to CVT minus A upon B plus some constant of integration U naught. Okay, it's a constant of integration that depends upon the initial condition. Constant of integration. Okay, so same way we can work out the expression for the du for the case of ideal gas. So for ideal gas, for 1 mole of ideal gas, we will have PV that is equal to RT, or P that is equal to RT upon B, which implies dP by dt at constant volume that is equal to R upon B simply. Okay, so again equation 5 and this result, let's call this as equation 7 and let's call this as equation 8. So equation 5 and 8 again imply that du, now it's for the ideal gas, du is equal to du by dt plus T dP by dt plus, so T dP by dt is R upon B, RT upon B minus P. What is P? P is this one. Okay, so minus, let me write in 2 steps. Okay, minus P and then dV. Okay, and this is equal to CV dt plus RT upon B minus RT upon B and dV. So cancel. So ultimately after integration, this implies integrated. Okay, so delta U that is equal to CVT plus some constant of integration U naught, which is a note that we can call it a U naught dash, because these they will be different. U naught and U naught dash, they are going to be different, which is a constant of integration. Okay, so this is our result.